So we have seen that how we can design an AVL tree. Now we will move for another type of special binary search tree, that is what we call threaded binary search tree. The question is that what is thread and why we are considering this thread. You see, if we have a set of numbers, for example, some set of numbers, I'm not writing a particular example. For example, let's draw a BST, say 10, 5, 15, say 1, maybe not 1, maybe 2, 7, 6, 12, 18, 25, something like this. Okay, so suppose some, and maybe say 14. Okay, so suppose this is a BST, and you see we have seen how we can recursively traverse each and every node for collecting the key values in each and every node. Now, if I ask you that instead of recursive solution, and also we have seen that in case of recursive solution, although the number of lines of code is very few, but there is a lot of job that computer has to do. If you have missed that, you can go back to my previous video where I have shown you the recursive solution of recursive approach of traversing in a node. So now you see one thing, that if I ask you that without recursion you have to visit this set of nodes, then what will happen? Somehow we have to actually store all these addresses of the nodes, because if I start journey from here, let's take an example. The address of this particular node is 100, this is 200, this is 300, and then we have something null, and maybe this is 400 and 500 and many more for our other nodes. So now we will start journey from here, right? Because this is our root, and you see this connection is basically unidirectional. Unidirectional in the sense that in each and every node we keep the address of its child, but we don't keep address of its parent. That means if we stand here, you can easily jump to this left child or right child, but if you stand here, you cannot easily go back to its parent. Now, if you want to do any order traversal, for example, Inorder. Okay. So in case of Inorder traversal, after printing all this set of nodes, you have to print this 10, and then you can come in the right side. That means when you are taking one direction in the bottom towards the bottom of the tree, somehow you have to keep a path some way so that you can go back to your root, and then you can change your direction again. So naturally the complexity of the problem will increase. And second thing is that, you see, if I consider printing this, say, printing this uh, in, for example, suppose say pre-order, pre-order. In case of pre-order, what will be the order of these values? Obviously, I will start from 10 because in case of pre-order, node is visited first, I mean printed first, then it's left, then it's right. So 10, then 5, then then 2, then 7, then 6, and then 15 will come, right? So now this part is very important. 6 to 15. Why I am saying I have marked it? Because you see, just we have seen that somehow we have to take a pathway so that I can go back. Now you can say that okay, I will somehow remember the previous the address of its parent. For example, when you are standing here, when you are jumping from this node to its left child, you have to store this 100 somewhere. Then when you are jumping from 5 to 2, you have to store 200. When you are jumping from 5 to 7, again, I mean same thing, 200. When 7 to 6, 400, like this. You can store. And now when you want to go back to the root node so that you can go to 15, from and you are standing here, you have to pick up 400, you will come here, then you have to pick up 200, you will come here, then you have to pick up 100 so that you can come here. So that means although visiting the nodes 7 and 5 is unnecessary, but we have to do it because I don't have any key, I don't have any way to store the address of the root directly in this 6 node. That means this tree is a very small example. If we consider a tree having very large height, at that time for going back from the leaf node to the root node, visiting all the previous n number of nodes where n is very large is going to be useless, and obviously which will kill the time. That is why the concept of thread comes. This threaded binary search tree actually gives a solution of this situation, this problem, that you can store some nodes which is not its parent, maybe in the root, maybe some nodes which is more lower level than its parent directly. How we can do this? Let's see. So before we consider threaded binary search tree, we have to understand two things. One is in-order successor and another is in-order predecessor. You see, if we just do a in-order search, in-order traversal of this particular BST, it will become something like, it's very trivial, you can easily do that. That is 2, 5, 6, 7. We know that if we do in-order traversal, it will become an increasing order, right? So 12, 14, 15, 18, 25. In-order successor mean the node that comes after a particular node in case of inorder traversal is called the inorder successor node. For example, 12 is the inorder successor of 10 because 12s come after 10 in inorder traversal. You see, not in pre-order traversal or post-order traversal. And inorder predecessor is just opposite. In an opposite way, you can say 10 comes before 12. That means 10 is inorder predecessor of 12. So now, this inorder successor and predecessor we can store in a particular node, in a modified node actually. In the threaded binary search tree, what we are going to do, we are going to store the address of their inorder successor and predecessors. So that means let's do one thing. Let's try to realize with the example. For example, let's take a very small number, small tree. For example, say 5, 10. Oh, sorry. That's should not be 10. Cannot be 10. Only this part consider 10, 5, and 15. If this was the tree and its inorder traversal is 5, 10, 15, you see 15's, there is nothing before 15, right? There is nothing before 15, blank, and there is nothing after 15. So 5 doesn't have any predecessor. At the same time, 15 doesn't have any successor. I mean, nothing is inorder successor of 15. And one more thing, that is, in case of this situation till now, in case of BST, let's draw it here. If the node value is 5, 10, and 15, we consider that, and if we consider designing a BST with respect to the exact address, considering some address of these nodes, it will look something like, so this is a node, two part obviously, left and right child. This is another node for 10. This is 5, and in this side we have for 15, sorry, right. And if we assume that the address of this particular node is 100, address of this node is 200, address of this node is 300, that means this part contains 200, so that it can point here. This part should contain 300, so that right side of this node can point this node. This is null, this is null, this is null, This is null. Now this null can be, can be utilized for this in-order successor and predecessor. Not only null, other cases also. We will see very soon. That is, if we take the in-order traversal for this node, it will become something like 5, 10 and 15. So whenever you will try to build a threaded BST, then the structure remains same. There is no change in the structure, but the connection will change a little bit, some connections. For example, if we just let's draw the nodes here first. So it is for 5. I'm sorry, I mean in previous case it was 10 actually. I'm sorry, I had a mistake. In the previous case, just we have written here that was 10, 5, 15. So by mistake, it should be 10, it should be 5. Yes. So here it is 10. In the left side, we have something 5. Here we have something what we call 15, obviously. And assume the same situation. The address of this node is 100, 200, 300. Okay. And root obviously will point its left child and right child. So this contain 200 and 300. So that it can point this node and point this node. But what we can do, we can utilize these two parts. You see, with respect to the Inorder traversal, it is 5, 10, 15. So this address 100, you see, 10 is Inorder successor of 5, right? So that means what I can do, the right pointer that we have here, we can utilize this right pointer for storing the in-order successor of the node. That means what will happen, I will store 100 over here instead of null. So what benefit I will get? That is, I can directly go from this node to its parent. So now it is pointing to previous node. Similar thing happened for the left part of this 15, because 15 has left in-order predecessor, and the left pointer can point in-order predecessor. That means there is two options. The right pointer can point either right child or in-order successor, and a left pointer can point either left child or in-order predecessor. So this 15 will now not null, rather it will contain address of this one, because 10 is in-order predecessor of 15. So I will store address of 10 in the left side of 15. That means here it is 100. So it can point this node. That means somehow if I come here, I don't need to think about to go back. I don't need to store this address 100 before we jump from this node to this node. because I will get this address as the left child, left pointer, from the left pointer of this node. Now naturally question will come, what about these two part? Always remember, as I just told you, that 5 doesn't have any in-order predecessor and 15 doesn't have any in-order successor, and that's why in case of a threaded binary search tree, only in these two extreme side case, in the extreme left doesn't have any in-order predecessor, and in the extreme right, that is the maximum number, does not have any in-order successor. That's why only in these two cases it will become null. But it is not true for the other numbers. For example, if we now try to draw a threaded binary search tree, how it will look like? Let's see. Suppose we have some set of numbers. Let's take some arbitrary value. Say 10, 5, 15, 2, say 2, then 7, then 20, then 18, then say 13, then 14, like this. Okay, something like this. So suppose this is the set of numbers. So we have to create a binary search tree which is threaded. It's a not simple binary search tree. That means it will not become only something like this. It will have some feedback line. Basically something like this that we have just seen. This is the feedback. So let's draw it. So one by one, as we have seen in case of AVL tree, that we connect a particular node in the existing tree, then we find the balance factor. According to that, we correct the tree, and then we proceed for connecting another node. In a similar way, this connection will get updated as soon as this new key value will be inserted in the tree. It's not something like we will create the whole tree and then we will connect them one by one. So because as a programmer you doesn't have any idea that how many data will come to you. That means whenever a new data is coming, you have to adjust the tree accordingly, and you can wait. If the other data come, then you can just do the adjustment again. So you see, let's just draw it. So we have only one node here, 10. That is fine. That is still no problem because it doesn't have any in-order successor. It doesn't have any in-order predecessor. So this is null. In this two side, you can say two side is really null. In the two side means the right and left pointer of this 10 node, right? Now I will insert 5. So 10, this left side has been replaced by 5. As soon as it is replaced by 5, now the in-order become, I'm just since it is the first time I'm showing you, that's why every time I will draw the Inorder Traversal so that you can you can understand, you can map what actually feedback line is drawing and how it depends on the Inorder Traversal. So in this case, Inorder Traversal become 5 and 10, right? So naturally 5 has a Inorder successor, and 10 has a Inorder predecessor. It doesn't require because 10 already have a left child, so Inorder predecessor is not required. So since 5 has a Inorder successor, now the right child that we have seen, Inorder successor is present in the right and Inorder predecessor present in the left, right? So that means in the right part of this 5 will now not null, rather it will become point to the Inorder successor, that is its root, and left part will not point anywhere because in the left of 5 has nothing. So that's why it will point to null. Fine. Now if we connect more, for example 15, now what will happen? The situation is something like this. I mean, just a minute. Five. Then here I have 15. And now you see, obviously this left will become null. This right of 15 is null, that we have seen. And the just previous situation we have just discussed will arise. Right? Which is right child of this one is will point 10 and left of 15 will point this 10. Right? Because now here the Inorder traversal was 5, 10, 15. Right? So if we continue again, we had a situation. Now we will point. We will set to 2. That means 5. I'm sorry. It is not 5. It should be 10 actually, right? It will become 10. And you see, since now 5 has a left child, now 5 left will not point to null. 5 now has a left child. So whatever null we had in the left of 5 was because of there was no Inorder predecessor. Now has been replaced by a left child. Now it's okay, fine. Now what to do? So what to do? We can say that this part, its side remains same, so it become null, and it will point its left child, and 5 will now point the right of 5. In this situation, the Inorder traversal will become 2, 5, 10, and 15. So 5 now still have 10 as its Inorder successor. So there is nothing in the right side of 5. That's why 5 can point its Inorder successor. If there was something in the right of 5, then it will not point. This is what I just said, that all the null will get replaced by its Inorder successor and predecessor. Okay. So, and similar situation for 2 to 5, because 2 has Inorder successor 5. That means right side of 2 become, will point to 5, and left of 2 will null. What we had in a previous situation in case of 5, the same situation will now arise for 2, because now 2 is the minimum data in the extreme left. So again, if we proceed for inserting 7, what will happen? 10, 5, 2, in this side 7, in this side 15. So naturally right side of 15 will become null, and left side of 15 is point to this 10, because left side of 15 is still not busy. And since now right side of 5 become busy with a new node 7, this right, the Inorder successor has vanished now, because it is no longer required, because ultimately now it's something like 2, 5, 7, 10, 15, where 5 Inorder successor is in its next level. That's why it's no longer required. But in case of 7, now it is required, because 7 has blank in the right side. That's why 7 right, that is 10, will now, instead of 5, now 7 will point to 10. and left side of 7 is 5. Left side of 7 is also blank, so it will point 5, and similar situation for 2 remains same, and this will become null. Now you see, in previous situation, in case of a normal BST, if we draw, it is something like only 10, in this side 5, in this side 2, in this side 7 and 15. The structure remains same, but since there is no feedback connection, that means if you jump from here to here, then here to here, what actually you are doing, you are storing these addresses one by one. So when you will try to go back, you cannot go directly to 10, rather you have to go to 5 again and then 5 to 10. Now revisiting this 5 is useless. To avoid this revisiting part, actually this thread has been created, and this is what actually thread is. Okay. So as soon as the number of level will increase, naturally the number of useless visiting will increase. To remove this number of useless visiting, actually this particular thread has been created. Okay. So now naturally question will come that how we will understand that a particular address that is stored in the right side or left side. So one thing is clear, if you closely watch a threaded binary search tree with respect to the address, you will see that other than the right pointer of the rightmost node and the left pointer of the leftmost node, all the right and left pointer of other nodes are busy with some address. For example, let's draw this one. Okay, so we have a situation like this: 10, 5, 2, 7, 15, right? So 5, 2, 7, 15. So, and situation is something like 15 is pointing here, it's null, it's pointing here, it's pointing here, it's pointing here, and it's null, right? So actual situation, if you try to reflect, so let's draw the nodes for each and every key values. It is something like, suppose this is node for 10. There is a node for 5 now here. There is a node for 2 here, suppose. There is a node for 7. And here we have a node for 15, right? The same structure I have drawn. Now here we will see about the addresses. Sorry. Suppose address of this one is 100, this is 200, this is 300, this is 400, this is 500. And you see, in the left side of this one, obviously will be 200, and this is 300. It will point to this node. Left side of this one will become 300 because left child. Oh, sorry, 500, not 300. Okay, and right side of this one will be 400, so that you can point the left and right. So now other part is left because they are should be null. According to the binary search tree, this part will null. Now we know that Inorder Traversal is 2, 5, then 7, then 10, then 15. So obviously 7 has Inorder successor 10. This 7 has Inorder successor 10. So that's why it should point this node. So that means the right side of 7 will be what? 100. So that it can point this node. Similar situation for 15 to 10. That is, left side of 15 should be 100. So that it can point this node. Similar situation for left side of 7, because left side of 7 is 5, right? So that means left side of 7 should, instead of null, it should be 200, so that it can point this node. And similar situation for 2, because 2's right is 5. I mean 2 has another success at 5. So right side of 2, instead of null, it should become address of 5, that is 200. So that it can point this node. But there is nothing in the left of 2 and nothing in the right of 15. That's why only these two parts will become null. So this is what I just said, that other than this extreme right and left node, I mean left pointer of the left node and right pointer of right, I mean extreme right node, all the nodes will have some address in its left and right side. Now it will make a confusion that the address present in the right pointer, is it the address of its right child or is it the address of its Inorder successor? Because we have already seen that this right pointer contain either child or successor. Left pointer contain either left child or predecessor. Now as a programmer, how a program will understand? How a program will understand that the right side, right pointer of 7, that is right pointer contain 100, is this address of the right child of 7 or a Inorder successor of 7? Because if by mistake there is a there is a misconception about these two, if the program wrongly detect or wrongly understand, then what will happen? As a programmer, you will try to go deeper level, but you will go actually upward. Like, just try to realize it, that by mistake you are thinking that the right side of 7 address 100, that is at right side, right child of 7. If you think in this way, and if you are standing here with a pointer P, and if you write P equal to P right, maybe you are thinking that you are going downwards, because P equal to P right means you are going downwards, right child, but actually you are going upward, because this particular address is the address of the Inorder successor of 7, which is the root. So your static, any misconception will lead to a very big failure at the time of traversing this node, and that is why somehow we have to keep understand that whether this is right, address of right child or successor, whether this is address of left child or successor and predecessor. That is why actually first of all how we can do that? We can use here the concept of flag. The 3 compartment that I can show here in this node, actually the node should have 5 compartments. You can say one is data, one is right pointer, left pointer, and here we have right flag and left flag. the purpose of right flag and left flag is same. What I mean that right flag you can consider as equal to say 0 signify that it contain address of say right child. If it is 1 signify address of Inorder successor. Similar situation for left flag. If left flag is 0, it signify address of left child. And if left flag equal to 1, it signify address of Inorder predecessor. So that means this flag will always remain become updated as soon as a new node will get inserted in the tree. It's not like all the tree will be created, the threads will be connected, and then the left flag and right flag will be updated. So this updation of left and right flag will be done in each and every iteration at the time of inserting the nodes in the tree. So this is all about the concept of threaded binary search tree. So we can stop our class over here. We will start in a different concept from the next day. Thank you.